So, a very good morning to all of you. Good morning and welcome to IIT Bombay. This morning we are going to have a workshop jointly organized by VJTI Mumbai and IIT Bombay as a part of your activity at VJTI. So, we had planned this to be a joint program between what we call the knowledge incubation under TEQIP at IIT Bombay and the program at VJTI. The background of this is that we would like you to be exposed to the kind of activities that we have in signal processing at IIT Bombay, and in particular I believe your course relates to biomedical signal processing, and therefore, we would like to talk in a large way about some of the things that we are doing in biomedical signal processing. In particular, I shall have one of my graduate students, Sagar, he is there. You can come, Sagar, come here. Sagar Sudhakara will be presenting his master's work, which relates to proteomics and the use of image processing in proteomics. So, he will be talking about that. Subsequently, we planned an exercise on an image processing software, and Sagar has very kindly put that together for all of you. In that exercise, he will first guide you through some elementary operations in image processing, followed by also a demonstration of how you could use it for the purpose of biomedical signal processing. So, that is what Sagar is going to do for you. I also have my teaching associates, you can come forward. This is Pushkaraj Shirvalkar. In fact, Pushkaraj happens to be an alumnus of VJTI. So, he did his undergraduate program from VJTI and he is now with us as a research associate in the TIDSP lab where you are right now. Pushkaraj will, together with Gauri Shankar Samal, he is you can introduce. Gauri Shankar is a faculty member in Odisha. He has come on a QIP program for his MTech at IIT Bombay, and he is also working with my supervision. And in fact, he has Pushkaraj of course has a lot of exposure to digital signal. In fact, he has been guiding the digital signal processing laboratory for the last 2.5 years, and Gauri Shankar has also been working on a specific processor, called the Raspberry Pi. So, he has, both of them have a lot of knowledge and they can expose you to how to use these dedicated processors. But what we can do in this short while for you is really to give you some basic exercises on a digital signal processor. We felt that since you are visiting IIT Bombay, you must actually get exposed to working on a real time processor. So, Pushkaraj has very kindly planned something interesting for you in terms of some basic some of you might have used digital signal processors, but some of you, how many of you have used digital signal processors before? Yeah, Vikram has used, some of you may have used, but everybody has not used. So, I think it will be a good exposure for you, to actually work on a digital signal processor and do some basic things. So, we thought that should also be a part of this interaction, and so around 3 I think we will be concluding this in this workshop, and then we shall immediately begin with a presentation from Sagar, followed by some exercises being done by you on image master, and then some exercises on the digital signal processor. Right. So, this is the plan for today. Now, it gives me great pleasure to welcome all the faculty members from VJTI who are coordinating this course. Let me begin by giving them some mementos. So, Rahul, and Professor Rahul, Professor Vikram Kehri, and who are the other faculty members who come? Professor Patil, please introduce your faculty. Professor Patil from VJTI.
Professor Megha Fernandez.
Yes, please come.
Professor.
Well, Professor.
Yes, thank you. Professor Pankaj Bakhotwar. Thank you.
Yeah. we'll, yeah. So, we now begin with our teaching associates. Sagar Sudhakara, I must introduce him. He is a master student in a student of the MTech program in the Department of Electrical Engineering, and he has been working on the theme of image processing in proteomics, specifically applications of wavelet based methods in proteomics. So, he will now of course be giving you a detailed presentation on that whole subject initially, and we welcome him and we of course appreciate his efforts. Okay. We have Pushkaraj Shirvarkar has been working very hard to carry out all the activities of this lab, and in fact, he has always been putting experiments together for several such workshops, and he is doing that today as well. And I have Gauri Shankar Samal, who is a master's MTech student in our department, and he is also a faculty member in an institute in Odisha, and he has also been working on a specific processor called the Raspberry Pi related to video coding. Now, he can also give you some insights. He might come around and help you with your understanding of the digital signal processor, and he will also, if possible, if there is time, he might also show you, or you can contact him and see what he is doing with the Raspberry Pi. Right. Now, I would also like to, this is one occasion we must also thank our CDEEP staff, because they have also been doing a lot of work and they remain in the background. So, I will first call upon Pallavi. So, Pallavi keeps organizing a lot of events and making arrangements. This is a little gift for her. And Pallavi, you must introduce all the staff. Come, and you should learn to do that. Yeah, call upon all the staff and introduce them.
Hi, I am Pallavi. I am working CDEEP office. All TEQIP workshop handling and TEQIP event workshop.
And she takes care of the TEQIP, organization of TEQIP events, logistics.
Thank you.
You must also introduce the other staff one by one.
First, Swapnil More.
Hi, my name is Swapnil More. I am working in CDEEP in last 4 years, working here as a technical assistant. Thank you.
Next, Mahesh Khadi.
Hi everybody, I am Mahesh Gadi. I am working in CDEEP since last 5 years, and I am working as a project technical assistant in CDEEP. Thank you.
Ajit Mhatre.
Hello, I am Ajit Mhatre. I am working as a project technical assistant for networking and other troubleshooting. Thank you.
I will take this opportunity to say a vote of thanks, and as well as I would like to give a token of love and respect to Professor Gadre. So I request Professor R.A. Patil, and please give us a token of love from VJTI to Professor Gadre.
So, with that little short and sweet introductory program, we will now proceed. So, what I will ask Sagar to do is, we can begin your presentation. We can start off with a few basics for about 10-15 minutes, and then we will proceed for high tea, because that would be served, and we will come back and continue and complete the presentation. Right. So, we will, because we should start the program soon enough. Right. So, we would like to start first.
Good morning everyone, I am Sagar Sudhakara. I am a student under Professor Gadre. I am working on application of signal processing on 2D gel electrophoresis images. So, I am going to use many signal processing tools like wavelets, controllers, SVD and other stuffs to work on this 2D gel electrophoresis images. So, what is this 2D gel electrophoresis images? So, there is a field called as proteomics, which deals with large scale of proteins, large samples of proteins. So, to understand those, this 2D gel electrophoresis is a technique used to study that protein expression in that field. So, what we do is, why this 2D? What is this 2D? Two-dimensional. So, we are applying electric field in one dimensional and gradient of pH in another dimension to get a 2D image. So, the name 2D gel electrophoresis images. So, this 2D gel electrophoresis images is a technique used to study this proteomic subject, and the protein spots are obtained after the application of electric field in one gradient in one dimension and the application of pH gradient in another one dimension. So by application of just the electric field in one dimension, we get image as like this, and then application of pH gradient in another scale, we get a 2D gel image. So by the application of electric field on the basis of their isoelectric points, these protein spots get separated. By the application of gradient of pH on the basis of their molecular weights, they go and settle down to their respective places. These are all protein spots on a non-stationary background. We can see how much the background is distorted here. So the digital image of the gel is captured for computerized analysis. We get this image, and then we have a camera. We take the digital image of that 2D gel image and then use it for further analysis. We need to do segmentation, denoising, and all the other stuffs on those digital image. So a complete automated system is required for this stuff. So this is how a 2D gel image looks like with dark spots. Those dark spots are protein spots on this nonlinear background, and that intensity level is the third dimension. So this is the system setup in Bark. This is the complete automated system. This is spot picker robo, where we take image from this camera of this 2D gel image and then analyze it in this PC. We do first denoising, then segmentation, then registration, and then these instructions are given to the motor and the spot picker robo. This spot picker robo goes to that respective positions of this protein spots, then separates it out, then sent to mass spectroscopy to analyze whether these are true protein spots or not. So this is the complete automated system which is there in Bark. So what are the applications by doing this? So if we find out there is a new protein spot in this 2D gel electrophoresis images, if we come to know that this is a new protein spot which was not existing in the previous gel images, this protein spot may be a disease causing protein spot. So if we recognize that this is a new protein spot, we can devise some drugs for that. So devising new drugs, even if it is a food, and if we find out that this is a new protein spot existing in that food, we can improve the food quality by knowing about that protein spot, even monitoring the environmental pollution, and then drug development and disease prognosis and diagnosis. Like if there is some kind of breast cancer and we come to know that this is the protein which causes this cancer. So this is the cancer tissue and this is the protein which is causing the cancer. So we can devise drugs for those stuffs. Now what are the problems? Now we know the application, what is 2D gel images, then what is the problem? We can just take the image and start doing the analysis part. So the major problem is we don't get proper images of those 2D gel because there might be uneven background and streaks. So when there is uneven background and streaks, we may not be able to recognize whether this is a protein spot or not. So to recognize that, we need to do proper denoising. There might be even overlap spots and saturated spots. When there are two overlap spots, we will not come to know whether there is 2 spots or 3 spots or many spots which are overlapped in that one particular spot. So overlap spots and saturated spot is one of the major problems. And there might be faint spots and artifacts. So while doing denoising process, we might lose these faint spots. So we need to see that we do not lose faint spots, and we do not introduce any pseudo spots also. We do not introduce any artifacts, and we recognize those pseudo spots as protein spots. And there can be some large and unstructured variation in spot indices, that is vertical and horizontal streaks which exist in the images like this. Vertical and horizontal streaks. These are not protein spots. So we might recognize those as protein spots. We need to see that those are eliminated in our denoising and the segmentation process. So these are the major problems: overlap spots, faint spots, background noise, geometrical distortion which appears in our image, horizontal and vertical streaks, spots on streaks, and saturated spots. Saturated spots are almost like the overlap spots. There might be more than 3 to 4 spots in this particular region itself. So we need to analyze how many protein spots are there. We have devised few methods where we can see that there are this many protein spots, and we need to separate it out. We even find out the location of those protein spots, then the spot picker robo goes and picks it up. Now steps, what are the major steps involved in 2D gel image analysis? I have presented it in detail so that you people can go through it once. So the image pre-processing, first is the image pre-processing step. In the image pre-processing step, what we are doing is we are going to denoise the image first. We are going to remove the artifacts, and then we need to highlight those stuffs which are important for our 2D gel electrophoresis image analysis. So the first thing which we are doing is the image pre-processing. So denoising, artifacts removal all comes under the pre-processing step. Next is the spot segmentation. After denoising, we need to segment out the image, so that it's almost like cutting the image into pieces, so that each piece contains one protein spot. So there should be accurate spot segmentation so that we'll come to know that these are the protein spots. Then is the modeling and quantification. So whether this is a protein spot or not, to detect whether it is a true protein spot or not. Then is the image registration. We need to do image registration so that we can match two images, and then we can say, okay, these are the two corresponding spots in all the other gel images, and we can align those images, and then we can say accurately, okay, this is the true protein spot, and if there is any new protein spot, then we can send it for mass spectroscopy and detect new spots there. And then identification and differential expression, and comparing with the already existing softwares to see that what we have devised is better than the already existing softwares. So we need to compare that. So the first step in this 2D gel electrophoresis image analysis is the denoising step, denoising of proteomic 2D gel images. So there are two kind of noises which affect our images. One is the additive noise, another one is the multiplicative noise. Additive noise is independent of the image. It's present all over. So we can remove it easily by just doing filtering. But the problem occurs when it is affected by multiplicative noise. Multiplicative noise can be non-isometric, short noise, and it is a byproduct of the stochastic nature of that image. So removing that is not easy by spatial filtering, because it depends on the spatial distribution of that image. So we need to model that 2D gel images to remove this multiplicative noise. The problem arises when there is multiplicative noise which is affecting our 2D gel images. So necessity of denoising. So additive noise we can remove it by spatial filtering, but spatial filtering has a problem. It even removes the edges. So we need to preserve those singularities. To preserve those singularities, we should use some other systematic methods other than the simple spatial filtering. So spatial filtering is not a good method. So there must be a trade-off which must be maintained so that we preserve the singularities as well as suppress the noise. So good denoising process must remove uneven background and high frequency in the image. Salt and pepper noise should be removed. Salt and pepper noise is just the additive noise, it can be removed easily. Horizontal and vertical streaks, those are the multiplicative kind of noises. For that we need to use some systematic methods for denoising. So the denoising techniques. One is the wavelet shrinkage method. If you people have any doubts regarding the problem statement, then you can ask me. Is the problem statement clear? So because the next steps which I am going to explain are all algorithms to solve those problems. So yeah. This was the spot picker robo. So what is happening is, this is the camera, we acquire the image of the gel, then we do the analysis part in this PC so that we can denoise the image, segment out the image, and then make sure that these are the true protein spots. So what actually we are doing is, we are going to separate out these protein spots on the basis of electric field and pH gradient, and then obtain this 2D gel image. On that we need to denoise so that we can make sure that there are this particular protein spot, whether we need to say that this is a particular protein spot or not. So for that we need to do proper denoising and segmentation, and the problems which we faced are there can be uneven background, overlap spots and saturated spots, faint spots and artifacts, and even vertical and horizontal streaks. So these were the problems faced in 2D gel electrophoresis image analysis. So to solve that, there are few methods, and even I said that we can't use simple spatial filtering to solve this problem. So a trade-off must be maintained between noise suppression and preservation of singularities. To do that, we have some methods based on wavelets and even contourlets. So we will see those methods now. So the denoising techniques. The first one is the wavelet shrinkage. So how are we going to use wavelets to solve this denoising problem? To solve this denoising problem, we are going to exploit that compression relationship with denoising. What wavelet does is, this wavelet decorrelates that sparse signal and removes that insignificant coefficient by thresholding. So we are going to use a nonlinear thresholding on wavelet coefficient to denoise our image. So we are exploiting the relation between decorrelation and denoising. and this should not be confused with smoothing. Smoothing just removes out those it's almost like low pass filtering. So the edges are not preserved. So we have to preserve the singularities and then denoise. So motivation of using wavelets here. So decorrelating property of wavelet helps us in denoising our image, and noise is spread out equally among all coefficients. So that was the motivation for using wavelets, and we can remove the most insignificant coefficients in this signal, so that we can create a sparse signal. By this way, decorrelating relates to denoising. So we can see I have taken one 1D signal. This was the original signal. I have introduced noise to that signal, and this is the first scale of wavelet decomposition. Second scale and third scale, we see that only the singularity parts are maintained and these insignificant parts can be made to 0. So by this way we can denoise our image, and then we can reconstruct back to get the original image. So what kind of thresholding techniques can we use? We need to use a nonlinear thresholding technique, that is after decomposition, to remove these insignificant coefficients, we need to do thresholding. So there are two simple ways of doing thresholding, that's soft and hard thresholding. The name itself suggests that soft thresholding is, it doesn't kill each and every coefficient. It keeps some of the coefficients and sends other coefficients as it is. But hard thresholding, by the name itself, suggests that keep whatever is significant, then kill all the other part. So you can see the transfer function here, and this is the graph. Hard thresholding keeps the coefficient as it is above a threshold level t, and the other part is killed. But whereas the soft thresholding brings it down. So this is soft thresholding, hard thresholding. Soft thresholding in some ways are better than hard thresholding, but in some ways soft thresholding allows noise to be, noise gets creeped into our images. So how this image denoising algorithm is done using wavelets? First we find out the wavelet transform of that image, then apply thresholding on that image, remove those insignificant wavelet coefficients, and then compute inverse wavelet transform to reconstruct back our image. So the threshold determination, how do you determine these threshold levels? So for that there are many algorithms in literature, that is the Bayes string and visual string. We compute threshold by these methods. So it is already there in the literature, we are not going to discuss that in detail. And the threshold determination, if we compute if we find out that the threshold is very small, we'll get output very close to the input image, but it will still be noisy. And if we make the threshold very high, we might lose out some significant components. So we need to have a trade-off between this threshold and what significant coefficients we need to retain back. Various denoising methods in literature. One is the hierarchical relation across scales. So we are exploiting this wavelet hierarchical relationship. So how many of you know about wavelet decomposition of images? I just want to know. Okay. What is going to happen is, we have an image, so we need to decompose that image into different scales. So what happens is, when I think I'll show you practically in MATLAB toolbox later, but now I'll explain it on the board. So we are going to send that image through a low pass filter and a high pass filter. So when we send it through a high pass filter, we'll be just getting the detailed part. So we just get those edges and the noisy part, those stuffs we get. So we send it through horizontal, vertical and diagonal parts. These are all the high pass filter parts in the decomposition. Here again, when you pass it through the low pass, the one branch will be sending it through the low pass and the other branch will be sending it through the high pass. These are the high pass components, and when you send it through the low pass and then downsampling by 2, this is the decimated version. Decimating means bringing it to a low scale. So this is the low pass filter one. So we get the approximate version here, and this part is again sent through high pass filters. We again get detailed parts of this approximate level 1. So this is level 2 one. This is level 1. This is image decomposition using wavelets. As a overview, I have just given an overview. So we are going to exploit this hierarchical relationship to denoise our image. So what we do is, we first decompose the image by using wavelets, then apply a threshold at the nth level and detect where the noise is present and kill those noisy coefficients even in the children part, in the finer scales. So that is how we do denoising, and then reconstruct back the image using inverse wavelet transform. So this was the hierarchical relationship we have exploited. Instead of exploiting the hierarchical relationship, we can even take the ratio of approximate and detailed subbands. We know that noisy components, we have seen in this figure that only the singular components wavelet coefficients retain throughout the scale. At each and every finer scale, the singular component coefficients are retained, whereas the noisy coefficients have become very less. So when you take the ratio of this one to that detailed subband, when we take the ratio of the approximate subband to the detailed subband coefficients have increased. So the ratio keeps increasing, whereas the ratio of the noisy parts decays as we go through a finer scale. So that ratio decreases. Then we apply a threshold on that ratio. So that is what we are doing here. That's applying ratio of approximate and detailed subbands and then applying thresholding on that. Instead of using thresholding, we can even multiply them and then bring those apply the threshold on the multiplicative part, so that the noisy parts are very low, below a threshold level, and the detailed subbands are retained as it is. Then the next one, instead of applying a threshold, thresholding needs human intervention. We need to decide whether this is the proper threshold or not. We need to go through many trials, then decide, okay, this is the proper threshold for our image. Instead of doing that, there is a method where we model our image, we stochastically model our image and then use MMSE like estimation to obtain back our image x of k. Now if you have a signal y of k is equal to x of k plus n of k, we model x of k as Gaussian because when like I will show you in the MATLAB toolbox, our 2D gel electrophoresis images histogram looks like a Gaussian curve in all the subbands. So we have modeled our signal to be a Gaussian Gaussian signal of mean 0 and variance sigma square. So we model our signal x of k to be a Gaussian, and we see that n of k is also additive white Gaussian noise. So we need to get back x of k. So x of k is we obtain x of k using the MMSE estimator. So this is the thing. Initially we assume that we know sigma square k, but we need to find out, even we need to estimate this variance of this signal. So to estimate the variance, we are going to use the maximum likelihood estimator or the maximum a priori estimator, and then we obtain sigma square k, then substitute here and then obtain the denoise signal x cap k. So by using the stochastic model of our image, we are denoising the image. Then we have devised a novel method in denoising, that is using Quincunx wavelet to denoise our image. So what is the difference between this Quincunx wavelet to other wavelets is, Quincunx wavelet has a different direction of decomposition. So this protein spots match with the direction of this Quincunx wavelets. So we see that our results are more accurate compared to other wavelets when we use Quincunx wavelets. So our denoised image with Quincunx looks much better compared to other wavelets. I have shown the result here, and even the error value, the mean PSNR values, peak signal to noise ratio values are high for our Quincunx wavelet method. So Quincunx wavelet is better for you in this image, for this particular 2D gel electrophoresis image. Now we are coming to segmentation. We have done the denoising part. This was the pre-processing step. So now we have to cut down the images into different parts so that we can like justify that this is the particular protein spot which is causing the disease. So we need to separate out them into pieces. So to do that, we need to segment out the images. Yeah. Yeah. What kind of commands you want? No, there are commands. What they are doing is they are just going to apply a wavelet transform on them and then threshold it. So they are just going to use this thresholding techniques. But for they are going to use this median approximate deviation, those those techniques, and then they are going to apply thresholding on them. That is how MATLAB is doing. They are going to use this base string, visual string to threshold and then do denoising. They are not going to use any particular wavelet like Quincunx wavelet. For this particular image, we have seen that this Quincunx wavelet works much better than all those existing methods. And even this was also a novel method proposed by Rangurajan from UC Berkeley. He has proposed that having a stochastical model like this, will be able to solve this denoising method much better than the existing MATLAB method. Yeah, segmentation. So we need to segment down the image. We know that there are few problems related to segmentation. So there are two methods for segmentation. One is the discontinuity based method, another one is the region growing method, that is similarity based methods. In discontinuity based methods, what we are going to is, we are going to rely on the gradient information of the image, but this is susceptible to noise. So we are going to use the similarity based methods, where we divide the image on the basis of some predefined similarity criteria. We see that, okay, this belongs to this particular region, okay, this should be separated out and kept, and if this belongs to some other region, like depending on the neighboring conditions, neighborhood conditions, we divide the images into different regions. This is less susceptible to noise. So one of this region growing method is the watershed transform, which I will be discussing it. So the major challenges involved in segmentation is again the weak and faint spots. So weak and faint spots have been removed in denoising, then we will not be able to segment them out. So we need to see that this weak and faint spots are preserved, and then we get them in our segmentation output. And the other one is the varying and non-linear background, overlapping spots. So when there are overlapping spots or saturated spots, there might be 2 or 3 spots in that same particular position. So we need to make sure that they are separated out and then given a particular ID to each one of these particular spots. So these were the problems in segmentation. To solve them, one of the method in literature is the watershed transform method. So what watershed transform method is, like I'll explain you in a simple ways. You know, Mumbai roads during rainy season, like today when it rained, there are a lot of potholes. So water gets acquired in the potholes and the remaining water is nowhere here. So it's something like this. Water gets acquired, gets stored in that potholes. So what happens here, in our image also, there are protein spots, there are dark protein spots. Assume that I pour water on this image. So water gets stored here in this region, in those protein spot regions, and there's a region formed here, something like this. So watershed transform does the same. It's almost like water gets, these are dark spots, so water gets stored in those places and a catchment is formed. So this is called as a catchment basin with minima at that protein spot. So we're going to exploit this in this watershed transform. But there is one problem with this watershed transform. It's over segmentation. Even the noise can be assumed to be a regional minima and a catchment basin can be formed. So to avoid this over segmentation, we can use selection inner markers, that is human intervention is required. I say to that particular PC that there is a protein spot existing here, you need to segment it out. So a human intervention thing is required here, so that I have to decide whether there is a protein spot existing or not. So it's not a good method. So to solve this over segmentation method problem, I need to use something much better than this watershed transform. We know that watershed transform is good in dividing it into homogeneous regions. So what if I bring in this wavelet transform along with watershed transform to solve this problem? We know that wavelet transform is good at finding the singularities. So using this wavelet transform along with watershed transform to solve the segmentation problem. So that's what I am doing. There's a lot of mathematics part involved, I'll explain it in simple ways. So what we are doing is, we are dividing the image into 2 subsets, that is the foreground region F and the background region B. So we know that intersection of foreground and background will be a null set. So CBMK means the catchment basin of that region MK, and MK is the minima of that image I. So we have to divide into 2 subsets. If a pixel xf comma yf belongs to a foreground image f, then its intensity value should be less than the intensity value of the background. We know that 2D electrophoresis images are dark spots on a nonlinear background, that is white background. So the dark spots intensity value will be less than the background intensity value. So by this, we need to find out a threshold h so that we can divide them into 2 subsets. So there exists an optimal value h, so such that the threshold at level h is defined by this. Then finding out the intersection of catchment basins mk with the th of I, we get this subset foreground f. So to find out th of I, we have used the wavelet method. So we find out, we decompose the image using Quincke's wavelet transform and we obtain wjxy. We use this alternate the next scale value wj plus 1, take its scale product, we define this term as a scale product, use that to divide the images into 2 connected maxima sets, the horizontal connected maxima sets and the vertical connected maxima sets. These are the neighborhood condition. On this basis, we decide the optimal value h. We find out that this Cmax using this horizontal connected maxima set and vertical connected maxima set to find out the union of connected maxima sets, and then find out the optimal value of H so that we can divide the image into foreground or background. So by doing this, we have just divided our image into foreground and background. We have still not decided whether it's a protein spot or not. So to decide whether it's a protein spot or not, we need to do something more, and even we need to find out the faint spots in those images. To do that, so this is the flow chart of what we are doing. Original image, denoising, apply Kim-King's wavelet transform, then watershed transform on the low scale image, then using that wavelet transform segment out the image using our method, then post processing after that. So by doing this watershed transform, we are going to decide whether our method is better than the other methods by this parameter, spot efficiency. So this spot efficiency was proposed by this delta 2 method here. This software uses this spot efficiency to show that their method is better than the others. So we have used the same parameter to decide whether our method is better than them. So what does this spot efficiency say is total spots detected by this number of false spots by total spots detected plus number of missed spots. If there are more number of missed spots, then our spot efficiency decreases. So we need to see that all spots are detected, there is no missed spots in them. And number of false spots, we need to see that there is no pseudo spots. We don't introduce any pseudo spots and we say that okay, this is a protein spot or not. So we need to reduce this number of false spots and even as well as decrease this number of missed spots. By doing so, we increase our spot efficiency. So we have done this for 5 gel images and we have seen that our method works much better than this delta 2 method. We can see that we have segmented the image here. We have segmented out this protein spot here in our method. In their method, they have like the pseudo spot has been introduced in delta 2D, but we have seen that there is no spot actually here, and there is a spot existing here, but they do not find any spot here. So there are false spots also. Here we have seen that there is no spots here, but by doing improper denoising or improper segmentation, he finds that there are some spots here, but there are no spots here. So by that spot efficiency value decreases for delta 2D. Now experimental result comparison, original image, our method after segmentation and their method after segmentation. Here we can see that we have done a very good denoising here. The denoising method does not work well. So even the pre-processing step, the foundation, if it's better, then all your steps keeps improving. We can see our method works much better than the delta 2D. Now the another method, now using wavelet interscale ratio to segment out the image. So what we are going to introduce a new term here, that is the IDI, interscale discrimination ratio, which I will be explaining. What we are doing is we divide our image into texture, edges, background, and the noise which is affecting our image. So our image consists of these 3 components as well as the noise. So we need to separate out this image on these 3 parameters. So we describe a term called as the DP. There is nothing but almost the error function which we find out, 0 to W integral h of u du. So the histogram of a 2D gel electrophoresis images looks like a Gaussian curve. So I'll show you in MATLAB toolbox that our 2D gel electrophoresis images histogram looks like a Gaussian curve, or more closely like a Gaussian curve. So the histogram can be modeled something like this, k into e to the power minus u by alpha to the power gamma. If you put alpha is equal to 1 and gamma is equal to 2, it's almost a Gaussian curve. And our dp is defined as this, it's almost like the error function. In communication systems you must have learnt about the error function. So 0 to wtkj e to the power minus u square du. Then Mallet has said that by increasing the scale, the wavelet singularity components are evolved across scales. That is, we have seen in wavelets decomposition, the singularity parts where coefficients are high, whereas the noisy part coefficients are low when we go across the scales. So IDI increases for edges, but IDI decreases for noisy coefficients, because we are taking ratio of the j plus 2th scale with the jth scale. So this interscale discrimination information IDI increases for the edges, because as we evolve across the scale, the noisy coefficients value decreases, but the singularity components coefficients value increases. So IDI, if we do thresholding here, this is the IDI curve. if you have two thresholds T1 and T2, the part here belongs to the edges, this belongs to the background, and this belongs to the interior of the spot, which is constant. So this is the IDI figure. We see that edges have the high value, the white is the high value, background is the medium value, and the interior it's very dark, so it belongs to the left side of that IDI curve. Now we introduce one more term called as the ITP, interscale texture probability ratio, or the interscale texture probability. That is used to find out the faint spots present in our 2D gel electrophoresis images. So we have defined a term called as interscale texture probability. It is defined by this equation. So we set ITP min. We have to set a minimum value, that is 2%, which we have set. We have experimentally found out that it should be 2%, or else we will be missing out some faint spots, and we can see our results. That binary image where we have got we have done denoising much better and segmented out protein spots. You can see that it's much better than that Otsu, 2D Otsu method, where he uses the same, he has defined this interscale texture probability. We can see that our methods work much better than this 2D Otsu method with respect to this interscale texture probability ratio. So now to identify these faint spots, we are using an energy distribution model. So stable protein spots should have minimum energy compared to other background area. So whenever a person is stable, so he stays in a stable state, he is not excited, and his energy will be low. Whenever he is comfortable, like when you go to sleep, you are comfortable, your energy state is low. Similarly, with respect to the protein spots, its energy state will be low whenever it is in a stable state. So to find out those protein spots, we have modeled that energy curve to be Gaussian, and its weighting function to be also Gaussian, and this is the relation between their variances. And we see that the location of the spots can be found out by finding out the second order derivative of that energy curve, and whenever this is greater than 0, then this is the minima of that energy function. So by doing that, we find out the faint spots. So faint spots can be detected by if it is either completely or partially falling into the minimum energy region. And then how to find out the oversaturated spots and overlapping spots. When there are oversaturated spots or overlapping spots, we see that there are 2 or 3 more, like now this, by doing it with just other methods, we see that there are many protein spots here, but we don't know how many protein spots are. We need to segment out this into some regions. So we have to decide that. To do that, we fix a regional minima S min and a threshold TH high. So if it is greater than that TH high, we discard those, and if it is less than a particular size S min, then we discard them as saying that this does not belong to that oversaturated spot. So again, we need to fix this threshold for finding out this oversaturated regions. So for doing that, we have a oversaturated pixel count. We fix that oversaturated pixel count experimentally to be 2%. If it is less than 2%, we will miss the oversaturated spots, and if it is greater than 8%, then we will be even bringing out background minima to be as the spot. So we need to fix this OPC to do proper segmentation. So we can compare our result with the Melanese 7 and SIGMO results, which are present in literature. So we have seen that our methods segments out, and it does not have any false spots, nor it has any missed spots. It works much better than the Melanese 7 and the SIGMO results. And the parameter which we are using to compare with the Melanese 7 and SIGMO results are the error function, the mean error in spot area detection. So the error function is defined by sigma of DSI minus GSI by DSI, maximum of that DSI and GSI. DSA is the detected spot area, and GSI is the ground truth spot area. We keep one of the 2D gel electrophoresis images to be a reference image. So we know where protein spots exist. By that we come to know about the ground truth spot area, and detected spot area is by doing those particular segmentation results. We find out those spots and then use that in this mean error calculation. By doing that, we can compare those 3 methods. We have seen that our method has all spots segmented, and it is correctly segmented, and we have not missed out any spots. On this 3 basis, we can say that our methods works much better than the other 2 methods. But there is one problem with our method is it takes 12.5 seconds to complete our algorithm. whereas other methods just does it in 7 to 8 seconds. It takes less time because we have many number of iterations, so that is the reason why we are getting good results. So it is taking 12.5 seconds, but whereas the other methods have less number of iterations but has more number of parameters. So parameter setting is one of the major disadvantage in other methods. You need to decide, like the image master 7 which I am going to show, you have to fix 3 parameters in those for segmenting out. So finding out the correct parameter values to segment out the image is a major disadvantages in those other methods. We can see our proposed method has less error, and even for different standard deviation our proposed method works much better than the Melanie 7 and Sigmo. And these are the few results of segmentation. So the now current ongoing work which I am working on 2D gel electrophorese images are, instead of using Quincux wavelets, why should I use just wavelets? Wavelets just brings out only 3 major components, the vertical, horizontal and diagonal components. If I use contourlets, I will be able to decompose my image into many more directions. Like I can decide how many directions I need. So instead of using Quincux wavelet, now I am thinking of using contourlet transform, where I can decompose my image into many more directions and bring out this shift invariance by using non-subsampled contourlet transform. So I am not using any downsamplers or upsamplers, so there is no subsampling there, and I can remove my noise much better than the Quincux wavelet because it has many more directions to decompose. So this is how we are doing it. We have multi-scale decomposition, and using Laplacian pyramid we are decomposing into different subbands. We have got many more directions now. Quincux wavelet had just horizontal, vertical and diagonal directions. Here now we have many more band pass. And then we are using singular value decomposition on just the band pass images, on this band pass images. If you use singular value decomposition to denoise on the complete image, we are not getting good results. So we are thinking of using SVD after this band pass directional subbands to denoise our image. I think most of you will be knowing about SVD. So what SVD does is, if you have a signal X, it decomposes it to U sigma V transpose. So this sigma, this is a diagonal matrix sigma. So there are some insignificant components which are not required for our signal, which we can remove and still get back our image with a proper denoised image. So we are going to remove this denoised parts out. Let's make this insignificant component 0 and retain the significant parts. So by doing this we achieve this denoising. And then after denoising, we have seen that in many methods we lose out the edges. So we need to preserve those edges, we need to enhance those edges. To do enhancement, we are using this method where we are going to classify our pixels into strong edge, weak edge and then noise. And for the strong edge and weak edge, we are doing the edge enhancement. By doing this, we are enhancing our edges. Then after doing segmentation, I am thinking of doing the image registration part. In image registration part, there are 3 major components. If done properly, we get a good registration results. One is the distance vector, finding out the distance vector. Like if you have a reference 2D electrophorese image and we have target images, we need to find out, okay, this spot corresponds to the particular spot in the other image. That is how image registration is done. To align 2 images, we need to find out correspondence between 2 gel electrophoresis protein spots. To do that, we need to have a distance vector. So there are different distance metrics used in literature. One is the Euclidean distance vector, another one is the shape contrast distance vector. So I am thinking of using different distance vectors to solve my registration problem. And even there are many correspondence methods also. One is the closest neighbor correspondence methods, K closest points neighboring methods, and soft assign method, soft Gaussian vector method, and even transformation. We need to find out a transformation between those 2 vectors. So for that, we can use an affine transform or a spline transform. So I am thinking of using spline transform to solve this registration problem. And then if it converges, if we find out that this is the particular point corresponding to that reference image, then we can stop that transformation here and get this final T, or else keep iterating this procedure till we converge to that particular protein spot. So this is the image registration part which I am working on now. These are the references. So if you have any doubts, you can ask me.
How you went through, to begin with, you selected some part of the image or a global?
Global, this whole image. Yeah? Yeah, I'm thinking of using block-based SVD, not the SVD on the entire image. I'm going to decompose my image using contourlet. Then after applying this contourlet wavelet transform, I'll be using a SVD on those bandpass images. So by doing that, I'll be not removing all this insignificant coefficients at once. So I'll be using kind of soft thresholding on those stuff, on this bandpass images. So SVD works well when you're doing it on a block-based images rather than using it entirely on that image. No, it is not like entropy. It is like almost like probability. So probability 0 to 1. We find out whether a protein spot exists there or not, and then we get a binary image by doing so. So if it is less than a particular value, we give it assign 0, and if it is greater than a threshold, we assign it 1. Then we obtain that binary image and then segment out. Yeah. Just to see whether these methods work much better than those methods. No, yeah. SVD on this contourlet transforms. Just SVD won't give better results. That's sure.
Any other questions? No?
Will you share some of your papers?
Yes, sure.
Any other questions? Okay, then I think Prince, I think once again we give him a big hand. Very nice presentation. And now we will have completely laboratory sessions. The first session we shall have, I think, are you going to first demonstrate and then ask?
Yeah, I'll just show this wavelet toolbox,
Yeah.
and then I have few tasks for them.
Right.
They'll go through that software and they start doing it. Then I'll come and help them.
Father will guide you on how you will go through some of the image processing exercises. What we do is we first give a kind of exposure to how to do it, and then you will do it yourself. Right? Then we break for lunch, and then we come back and have a lab on this.
This is the wavelet toolbox. Here I'm going to show how wavelet decomposes the images into different scales, and I'm going to show you how those images look after decomposition. And then sir asked about denoising using wavelet toolbox, how it looks. I'll show you that. And then I'll show you the histogram of this 2D electrophoresis images, why I have modeled it as Gaussian curve. Then we can go to image master. So here I am using Haar wavelet, and this is on some image which I have taken to show image decomposition using wavelets, and this is a grayscale image which I have taken. Now I'm going to decompose it into two levels first to explain this part. So this is the image decomposition. This is the decimated version because we have a downsampling there. There is another one, image decomposition, where you don't decimate it and you get the image of the same size. But here we are decimating our image. These are the high pass filter one. I'm showing this particular one. We see that only edges are there in particular direction. The diagonal, the horizontal and vertical edge parts are just stored here. Diagonal detail coefficient at level 1 and the horizontal detail coefficient at level 1. This is how it looks. Now after low pass filtering, then applying high pass filter on those stuffs, you can see how it looks here. It gets much more distorted. And this stuff. And finally the low pass filtering at level 2. Approximation coefficient at level 2. This is how it looks after low pass filtering it twice. And then MATLAB has reconstructed back the image. This is the synthesized image. Now instead of using level 2, if I use level 4, this is how it looks. Again, do the same thing on this particular stuff. Keep doing it till you reach to that level 4. So this level 4 approximation looks like this. Approximation coefficient at level 4. Now by denoising using this MATLAB method, you can see that we get this kind of image. It's using just the thresholding technique here. I think we can see the what threshold it uses, I guess. So it finds out the histogram and then thresholds here. By that we are doing denoising here. Now I'll show you for 2D gel electrophoresis images. So this is a 2D gel image. I'll convert it into gray. I'm going to use Haar wavelet and again level 2. Let us see how it does. So this is the vertical detail, the horizontal detail, and the diagonal detail. So there are not many edges. So we need to see that the edges are not lost, because edges play a vital role here. This is the approximation coefficient at level 2. Now denoising using MATLAB method, that is the MATLAB toolbox method. Like it is almost like it has smoothened out the image. Not proper denoising is done. It's just thresholding the image. So we see that majority of the image consists of background. So there is a peak at a very higher intensity value. That's almost around 255. We have a peak. That means the image, majority of the image is background. Only few pertains to the particular protein spots. So histogram is something like this. So we can model it as a Gaussian curve. I'll show you in Image Master 7 why we model it as a Gaussian curve.
Because when I went to one of the doctor's field patient through my butterflies, and the doctor used the same terminology while discussing with me. These are some protein deficiency in the body that can be covered with the help of protein food like eggs, etc. He suggested me some of the capsules, contents like that. So therefore, give this body will get like that. I thought that he did that kind of. No.
So, good morning everyone. My name is Pushkaraj. I am a tech third year student. My specialty is communication engineering, and I am also a research assistant in TISP lab. This particular lab. So, first of all, actually, I would like to thank Professor Gadre, to give me this opportunity to discuss with you some of the things that we actually work on. So, I am not the only research assistant who works on this particular DSP processors. There are several other research assistants with us today. So, yeah, so I will talk about digital signal processors today. So, in general, we have listened throughout our academic course that in general analog signal processing should be done in digital domain, to obtain as much accuracy and as much speed possible in general. So, this you can say in general is the block diagram of processing any analog signal in general using a digital processor. I am not reached digital signal processor yet, but any general digital processor will have this kind of a block diagram in which we have an analog source signal. Okay, it is sensed through any kind of a transducer or a sensor in general, like a microphone you can say. Then we sample that particular signal to discretize that signal. We have not yet quantized the values of the signal, but we are just going on taking different samples at some discrete values of time. Then we quantize it so that we actually get pure digital signal here, pure digital signal, and then we process it. And processor might give some output to its output ports. Then we again dequantize it, because if you want to see the signal again, we cannot basically view anything in digital format. So, we again dequantize that signal, reconstruct it. Again reconstruction means just the opposite operation of sampling, whereas dequantizer is just nothing but opposite operation of quantizer, and finally we get the analog signal output that we wanted. Okay. Now, why digital signal processors? If a digital processor can do these things, then why do we go for digital signal processors? So, if we were to compare digital signal processors with any kind of general purpose processors that we use, let's say in any of Intel x86 or 8085, all those processors that we have learnt till now, and also the upcoming processors, the main differences between these two particular processors are as mentioned in the slide. So, typical applications that our general purpose processors can be used are nothing but generally involve data manipulation. So, let us say in applications where word processing or database management is required, we can just use a general purpose processor and we get our problems solved. So, there is no need of any special kind of a processor which actually does numerical computations very fast, because these applications are not that computation intensive applications. But let us say for example, take the application of a motion control. Let us say we have a robotic arm in which which basically operates on the images captured by the camera installed on a robot, and let us say the arm has to track a particular oscillating any kind of oscillating object, or let us say a falling object which the robot has to catch. So, if let us say our processing is not that fast, we are using some general purpose processor, then that arm might not track all those objects pretty clearly, pretty efficiently, and you may not be able to catch that particular object. So, that is where digital signal processors come. Now, what are the advantages of digital signal processors? They are optimized for the some arithmetic and data handling common operations, which are all common to signal processing applications. So, let us say consider a multiply and accumulate operation. So, we generally have to compute dot products. So, let us say we have two vectors or two signals in general, two digital signals, and we want to compute the corresponding multiplications and add them together. So, this is in general we can say as a dot product. So, this can be efficiently done using something known as a MAC, or a multiply and accumulate operation. Now, we can obviously do this in software, but DSPs are actually provided with a specific customized hardware in which this is efficiently implemented, so that you can actually converse with the hardware present on the DSP and perform these very fast as compared to general purpose processors. Again, what are other advantages of DSPs? We have you can use efficient memory access. So, I hope we all are know about von Neumann and Harvard architecture of processors. So, in case of von Neumann, basically we have only one complete memory chunk allocated to us. We use it either as a program memory, or as a data memory, or also as an IO memory according to users decision. But in case of Harvard architecture, we actually have a separate memory maps for data IO as well as program IO. So, implementation of some program cache memory is also very straightforward in that, because we have a dedicated memory map for our processor. So, these are again some advantages of DSPs which actually are helpful in real time processing in general. Pipeline is something I will say is common to the modern processors, modern general purpose processors as well as DSPs. These are some features of DSPs as well in general. Again, streamlined input output is another very important point actually in this case. So, when we say streamlined in general, what we mean is basically the input and output acquisition process in general is dedicated to some other coprocessor involved with this process, either coprocessor or some different dedicated hardware which can perform input output in parallel to the processing of the processor, which is going on inside the CPU. So, this streamlined input output is a very important advantage of DSPs, which actually we will see why it is required also in a few minutes if time permits, obviously. Again, specialist instruction sets, again DSPs, as I said in case of MAC and so on, these instruction sets are very useful, and also some customized implementation of time consuming routines can be done, such as FFT. FFT actually FFT is the fast algorithm to implement a DFT. So, if we implement this particular algorithm, or this or any other algorithm which is computationally very intensive, then we can actually gain a lot in terms of the speed of the processor. So, now actually to take you towards our processor, that the kit we are going to work with, I am going to just finally give an introduction about fixed point and floating point DSPs and some differences between them. So, in case of fixed point DSPs, they actually utilize a natural representation of numbers. So, let us say we have any integer or any floating point, it is treated as it is and then processed also as it is. Okay, this involves like the speed of execution is very high, because it is very much straightforward, but the accuracy suffers in general. In general, if you compare the accuracy of fixed point processors with floating point processors, the accuracy is lesser in case of fixed point, because we actually trade off this with speed of execution. But in case of floating point DSPs, they actually use a characteristic mantissa based representation of numbers. So there is a floating point. I mean, there is a bit dedicated to the sign of the number. Then some bits are dedicated to the characteristic part, which we obviously all of you must know, and then the fractional part, which is the mantissa. So then actually even the range of numbers that you can represent using a floating point format is very high as compared to fixed point, and also the accuracy is very high. But this there is a trade off with the time required to compute all such things. So now having discussed about this, now let's get started with our kit that we are going to use today, which is based on a processor, DSP processor by TI, named TMS320C 5515. This is a 55XX series processor. This is a 16.6 point DSP from TI. So yeah, that's all actually I had to talk about. Like, I want to just motivate today's lab session, why to use DSPs, and so that's why that's all things I have today. So thank you, thanks a lot. So yeah, so now actually I will request all my research assistants to give all of you kits, per one kit per PC, as well as a connector. So with that we can get started, get set up with the Code Composer Studio software that we are going to use. So meanwhile, actually go to the desktop of your particular PC. Create 2 new folders. Okay, create 2 new folders. Give one of them name as workspace, the workspace that you will be working on today, and the other one, the name you can actually give as VJTI, so that we recognize later that this was used as a part of today's TEQIP session. So create 2 folders on desktop. Name one of them as workspace. Has everybody a working PC with them? Second folder name VJTI. You can give the name of the college. Yes, one of the folders should be named as workspace, second as VJTI. Yeah, okay, so now you can actually follow me. I will show you what to do on my PC. iitb.ac.in/tilde ee352. Okay, if you can't see, actually we'll sit down. कौन सा ईट है? मेरा उल्टा ही है क्या, तुम बनाओ. और इधर एक मिनट, हाँ, कनेक्ट टू अ प्रोजेक्ट. हाँ, so and yeah, has everybody gone to this link, sharda.e. Please go to that. E352, E352, sharda.ee.iitb.ac.in /tilde EE352. EE352, EE352. First, yeah. So yeah, download the lab 1. Download whatever is there, behind the link lab 1. Lab 1. Scroll down to the bottom. There must be a link lab 1. Download a zip file present in that link, and download that inside the VJTI folder. Okay. So all the all the auxiliary material that you require today should be downloaded in VJTI folder. So let's wait for everyone to get on with us. So those who have downloaded lab 1, yeah, those who have downloaded, open the lab 1 handout file present in that, and so I will also open. This must be the, sorry, lab 1. So everyone can open this particular file. Its name is E352 lab 1 handout, and inside that, go through the introduction part. I will give you 5 minutes, from now, because we don't have too much time. So you can actually go through the introduction part and section 1.3, introduction to EZ-DSP 5515, that is the kit that we are going to use today, and Code Composer Studio V4 or version 4. It's not a very long section, but it is very informative. So I request you all to please read through section 1.3. Section 1.3 you can read for next 5 minutes. So I will now click on debug operation, so that this program will be okay. So it asks for a target configuration. So you can come back actually. So